She's a senior right now at Parkland. Last year she took AP Physics Level C, Mechanics and E&M. Me personally, one of the top students I've ever had. To challenge herself a little bit more this year, she went on to Lehigh University in the fall, taking quantum mechanics and getting an A in that, 4.0, and then also taking particle physics this last semester at Lehigh, also in the top of her class there. But without further delay, let's give Nina a nice welcome here. We'll let her have it.
All right, guys. So before we begin, I just want to let you know that in college, if you do happen to go into physics, special relativity is usually the introductory chapter to a lot of the physics courses, which is actually why I chose to present it to you guys today. So I hope you enjoy it. There are 3 sections to my presentation. We're first going to go over the history of special relativity, how people sort of developed these theories and these concepts. And then the second section is, once these concepts have been fully developed, what are the mathematical adjustments that we have to make for it? Then the third section just includes some interesting results and examples of special relativity that you can use to impress people when you talk to them at parties and whatnot. So let's start with the history of special relativity. Going back to the 1600s, the first question that people started asking with regards to special relativity is, what is the speed of light? Is it finite? Is it infinite? If it is finite, are we able to measure it? The first attempt to measure the speed of light was actually conducted by Galileo himself. He had 2 people stand on hills that were relatively far away from each other and then flash lights at each other and time how long it took the light to reach from one hill to another. However, his results were really inconclusive because the distances were too short and the speed of light too fast for him to be able to measure any time difference. So now the question becomes, if we do want to measure the speed of light, we need larger distance scales. But how do we get those on Earth? The answer is, well, you can't. A famous scientist by the name of Romer actually conducted an experiment in 1676. By that time, it was known that Io, one of Jupiter's 4 moons, was regularly eclipsed by Jupiter. What he could do was he could measure the time it took for information from the eclipse to reach Earth multiple times, take an average of it, and essentially measure the speed of light. You know the distance from Earth to Io, you know how long it takes, and then you can find the speed, of course. So he actually measured c to be 202.2 times 10 to the 8th meters per second. So the first conclusion that we can get from this is that the speed of light is finite and it is measurable. Also another interesting thing to note is that this is an extremely awesome measurement for the time. 1676, for someone to get so close to 3.0 times 10 to the 8th meters per second is absolutely amazing. So now we know that the speed of light is finite at this point, right? So let's think about what we know about things that move at finite speeds. So we know that depending on the reference frame that we are looking at, another object in motion, its speed changes, right? So if the speed of light is finite, we would assume that that would be also the case for light, right? Well, let's move into the 1800s with Maxwell's equations. So Maxwell actually developed 4 equations that combined the theories of electricity and magnetism. And essentially, the solutions to these 4 equations, shown on the right, are traveling electromagnetic waves, essentially light. And these equations actually provide for 2 properties of light. First, that light moves at a fixed finite speed c from a source in all directions, and that it also travels from a moving source at a fixed finite speed. Now, let's take a look at the second property, very important. It travels from a moving source at a fixed finite speed c, the same speed that it moves from a source that is at rest. So we know, again, from relative motion about the idea of velocity addition, right? If we're at rest and we see a train moving at 5 meters per second and a person on that train relative to the train moving at 3 meters per second, we would see the person moving at 8 meters per second, right? However, this is not the case, right? If light emanates from a moving source, we still see it moving at c. So obviously, normal relative motion does not apply to light, which is a little bit disconcerting for a lot of the physicists of this time. Now, in addition to this confusion, Maxwell's equations also claimed another thing, that light does not require a medium in order to propagate. So this also seemed a little bit odd to a lot of physicists because all of the waves that they were familiar with had required a medium in order to propagate. So all of these waves required a medium for propagation, and so it seemed odd to a lot of people to think that light just happened to be the single exception to what appeared to be a general rule. So instead of accepting the fact that light does not need a medium to propagate, physicists made up a medium called a light medium, which was named the ether. So they believed that Maxwell's equations would only hold in the ether and that we were in the presence of the ether, and so that's why Maxwell's equations ended up working in our situation. So the problem with this is that there was no experimental evidence for the ether whatsoever. People just made it up for their own comfort. And so for a long time, there was a lot of debate on whether or not the ether actually existed. So in 1887, two American physicists, Michelson and Morley, actually decided to test for the existence of the ether. Now, just ahead of time, their experiment actually disproved the existence of the ether. But I do want to go through a little bit of how they did this, because it is actually a very genius experiment that they did. So we personally are not sure of the existence of the ether, which means that if an ether exists, we don't even know our motion relative to it. However, we do know that the Earth moves in an ellipse, and we move at a speed of 18.5 miles per second on average. So our velocity, or our speed, would, in this case, would actually change relative to the ether by around 18.5 miles per second in a given year. So this would translate to an experimental effect of 10 to the power of -8. This is obviously a very small effect, so what they had to do is they had to find some sort of measurement device that could detect such small differences. And what they ended up using was an interferometer, which measures very sensitive shifts in light. So now, this is their apparatus. So they have a light source that shines onto a partially reflective mirror. Some of the light reflects upwards in the transverse direction to a perfectly reflective mirror, which reflects it back down to a detector. And then the rest of the light goes longitudinally to another perfectly reflective mirror, and then that kind of comes down, reflects off of the middle mirror onto the detector. An important thing to note also for this apparatus is that it was able to be rotated, so it could test every possible configuration relative to the ether by just sort of rotating this giant block that the apparatus was on. So this detector is the interferometer, so we obviously have two light waves arriving at the interferometer, and so that's how they would detect minute differences if there was a phase difference between the two light waves that were arriving at the detector. So now, if we were at rest with respect to the ether, you would have noticed that the two distances from the middle mirror to the top and the side mirror were both L, right? So the same distance. That means that light would take the same amount of time to travel both the transverse and the longitudinal paths, and we should see no interference whatsoever, right? But if we were in motion or in line relative to the ether, the travel time would differ between the two paths. So we don't really have a lot of time, so I'm not going to go through that math, but essentially the inline path, so the path that is in motion relative to the ether, would take a time ti, which looks like that. Where L is obviously the length that it has to travel, c is the speed of light, and u is the apparatus's speed with respect to the ether. The perpendicular path, sort of the transverse path that we had seen before, takes a time tp. And so they differ by a factor of the square root of 1 minus u squared over c squared. So they should be able to measure that phase difference when the two light beams kind of come out of phase to the detector. So that's of course detected through interference. But what they found was that no matter the configuration of the apparatus, no phase difference was detected whatsoever. If it did exist, this would be impossible, and thus the very solid conclusion was made that the ether does not exist. However, a lot of physicists still were not very comfortable with this idea of no ether, and so a famous physicist by the name of Lorentz actually tried to say something in order to save the idea of the ether, that the path that was in line with the motion of the ether had contracted its length by a factor of the square root of 1 minus u squared over c squared. That would actually change the two times so that they would equal each other and that the lights would come in phase, or the light beams would come in phase. So he actually did predict something called length contractions, which is a fundamental result of special relativity correctly, but for absolutely the wrong reason, which is a funny coincidence of the history of physics. So Now we understand that light moves at a constant speed c from Maxwell's equations, and that the ether does not exist, which essentially states that there is no absolute reference frame from which we can consider light. Now that we understand that, we also have to go back to classical relativity and Galilean transformations. So, let's say we have relative motion between two reference frames. We have one presumably at rest, that's just the normal coordinate system, O, and then we have one that is in motion along the x-axis only, in this case, relative to reference frame O, and they have prime coordinate systems. So, we can actually translate information, positional information and information regarding time, between these two reference frames. These are called Galilean transformations, and they look like this. So the position in the prime frame is equal to x minus ut, where u is the speed of the moving frame relative to the rest frame. And then since we have no relative motion in the y or z coordinates, we don't have any change. They are exactly the same, and the same for time. So what's interesting about these is that Newton's laws hold in both frames. And since we know that, we can conclude that Newton's laws can hold in any frame moving at a constant velocity with respect to another inertial reference frame. So these Galilean transformations are what's called the symmetry of Newton's laws. A symmetry is basically a set of transformations that when you apply them onto something, like let's say in this case Newton's laws, you just get that something back. You get the same laws back. So if you apply Galilean transformations onto Newton's laws, you basically get the same thing back. Things are constant, essentially. So now we have a symmetry for Newton's laws. And once Maxwell's equations came around, people were wondering, is there a corresponding symmetry for Maxwell's equations? There must be. So the problem was that Newton's laws do hold in Newtonian inertial frames, but Maxwell's equations actually do not. So they couldn't use Galilean transformations to help sort of explain Maxwell's equations. But thankfully, our good friend Lorentz came back and proposed a set of transformations that actually worked for Maxwell's equations, that were a successful symmetry. So this is what they look like. It's very difficult to derive, so we won't do that. You'll just look at them. And so u obviously means the same thing, the speed of one reference frame with respect to another. And so x here is one reference frame, and x prime is the one that is in motion relative to x. So you can see that it looks very, very different, right? But it's still trying to do the same thing, translate positional information from one reference frame to another. Now we think, okay, so which one is the true symmetry of nature? So obviously we see that for both Lorentz transformations and Galilean transformations, we're going from x and t to x prime, t prime, and then y and z to y prime and z prime, right? So people start to wonder, like, how do we translate our information from one reference frame to another? Do we always use Lorentz transformations? Do we always use Galilean transformations? Which ones are the true ones that we're supposed to use? So it was found that Lorentz transformations are the truer symmetries of nature, essentially meaning that Maxwell's equations are more fundamental. And so then it comes the question, so how come Galilean transformation seemed relevant before this? How come Newton didn't realize that there were these Lorentz transformations and those were the ones he was supposed to use? Well, let us compare the transformations side by side. In the 1600s, when Newton was doing his stuff, they could not measure anything at speeds of significant fractions of the speed of light. So essentially when they did their calculations, if you even applied it to the Lorentz transformations, you would essentially get the same result as if you were to use Galilean transformations. So for their situation, what they had concluded was actually correct. They just couldn't measure anything that was significant enough for them to realize that Lorentz transformations had existed, which is also pretty cool. Which is also why you learn this usually in your physics classes compared to this, because this is not really relevant, or no, this one's not really relevant for a lot of the things that we do here in high school and for basic physics classes in college. All right, so now we have all of this, right? We know that the speed of light is constant. We know that the ether does not exist. There is no absolute reference frame in existence. And we know that Lorentz transformations are more fundamental. And so in 1905, Einstein comes around. I'll put this down for you so you can start copying it. So Einstein comes around in 1905, and he proposes these two very much overarching principles or postulates of special relativity. The first is that the laws of nature assume the same form in every inertial frame. Basically, that physics does not break down if you are in an inertial reference frame, which is a very basic but very important statement to make, of course. And then the second one, which is more relevant to what we are considering, light appears to move at speed c to every inertial observer, essentially reiterating the fact that no matter what reference frame you're looking at a light wave from, it's always moving at c. Even if you are at 0.9999999 c, if that's what you're moving at, you'll still see a light beam moving at c. And that also, again, reiterates the fact that there's no absolute reference frame. Everything is relative. So it seems like most of us are done. So that was essentially part one, right? The history of special relativity. And the three things that you should most importantly take away from this is that the speed of light is finite, that the ether does not exist, so light moves at a constant speed relative to every inertial observer and the same one, and that the Lorentz transformations are the truer symmetries of nature. So now that we have this whole idea of special relativity developed, we understand that we have to make mathematical adjustments for physical observables, things that we observe, momentum, energy, velocity, etc. So actually, two of the most important results of special relativity are time dilations and length contractions. So we'll actually go through the derivation of only one today because we're in a time crunch, so I'll do the time dilations one with you guys. So the interesting idea of time dilations, let's say you consider yourself as the rest reference frame, right? And you're watching a rocket kind of pass by and someone's in there. The idea of a time dilation is that you will think that the person's time in the rocket is passing slower than what you perceive time to be passing for yourself, right? But the person in the rocket thinks that he or she is still in her or his reference frame, and so that they will think that time is passing slower for the person that they see moving on the ground away from them. So there's a little bit of an example with this image. So you see that the person, if the rocket is at rest, there's this sort of like makeshift clock where light is emitted from this bottom block, reflected off of the top block, and then reabsorbed by the bottom block, and that's considered to be 1 second. So up and down is 1 second. But if we're looking at the rocket, we see that the light has to travel a larger distance to reach the top block and then also to reach the bottom block again, which means that for us, their second seems a lot slower than our second does. Now, so this is the formula that we would use. T prime is what we think the rocket's time would be, and then T is what we think time is, like in terms of how much time has passed. And so, of course, we have our famous factor of square root of 1 minus u squared over c squared. And so now let's go through a derivation of this. So there are two different ways to actually derive this formula. One is a more conceptual way, and then the other is a more fundamental way using Lorentz transformations themselves. So we're going to go through the derivation through Lorentz transformations just because it is more fundamental, but if you want to see the more conceptual way, you can come up to me afterwards and I'll show it to you. So when we are deriving time dilation, there's one important thing to note. We have to think of our derivation as considering a situation of a particle moving from position xi to xf. So now we have two different time coordinates, right? So for a particle in our reference frame position xi and ti, moving to position xf and tf, in another reference frame, we see ti prime and then tf prime using just the Lorentz transformations, right? So now, in order to find delta t prime, right, which would be the time that we think passes for the particle, we would just subtract the two equations. See, we factor out the common factor, and then we have all this stuff in here. And so then we just combine tf prime minus ti prime into delta t prime, etc. So now we look at this, right? So we have this, and we look at what delta x means, right? So delta x is the distance that the particle travels in a given time, delta t, in our reference frame. So what happens is that we would see it travel a distance, delta x, in u times delta t, right? Its speed times the time it takes to travel, delta x. So if we make that substitution, we have a formula that looks like this. Okay? So what's interesting now is that we can factor out a delta t from this equation, and we can combine the two u's up there into this. So just while you're finishing copying that down, just a reminder of what is what, so you don't get confused, because it's very easy to get things confused. Our delta t prime is what is the time that we think is passing in that moving reference frame, and then delta t is what is actually passing in the reference frame, or like in a still frame. It's essentially a still frame in this case. So we were at this step, right? We factored out our delta t, given the fact that delta x is actually equal to u times delta t, where u is the speed. So now we have this situation where we have the same thing in the top and bottom. So we have the square root of 1 minus u squared over c squared in the denominator, and in the numerator we have 1 minus u squared over c squared. So that actually can just turn into delta t times the square root of 1 minus u squared over c squared, right? And so then to get to our basic formula that we had started from in the beginning, we just move the factor over to the t prime side, and there we have our time dilation formula. Note again that Lorentz transformations are a fundamental symmetry of Maxwell's equations, right? And Maxwell's equations fundamentally describe nature, which means that time dilations and length contractions later are actually very, very fundamental results of special relativity. There's no assumptions whatsoever. This is really very basic in a sense. So now we go into length contractions. So I won't derive this because you've already copied the other one down. So in addition to time dilations, we also have this thing called length contractions, and this is the formula for it. I will explain. So now let's imagine again we're in the rest reference frame, and we're watching a rocket pass by. So first, the rocket was on the ground, it was at rest, it's in the same reference frame as us essentially. So we measure its length, and we say, okay, it's L units long. But if it's moving, if it's passing by us, what we'll measure as the length of the rocket is actually shorter than what we had measured when it was still, right? And so obviously the faster you go, the more the length contracts of whatever item you're observing is moving in your reference frame. And so also notice that length only contracts along the axis of motion, right? So I made it so that the circles are actually all the same height because there's no relative motion in the y direction, only in the x direction, and that's why it only contracts in the x direction. So this is also another fundamental result of the Lorentz transformations. I will not go into it because we are kind of crunched on time, but essentially it's the same idea. You just use Lorentz transformations, subtract, and then just move a bunch of factors around, and then you would get your final result. Oh, and of course, just to explain, L prime is what you would measure the length of the rocket to be if it were at rest, and L is what you actually measure the length of the rocket to be as it's moving. Adjustments for velocity, momentum, and energy also follow from special relativity, right? And so I'm not going to go into the derivations of these because the explanation for why these adjustments have been made actually come from the idea of four vectors, Lorentz invariance, and a bunch of other stuff. That takes a long time to explain, so I won't do it. But just for fun, velocity, actually, we don't use normal velocity anymore in special relativity. We change it so that we measure delta x with respect to time in a rest reference frame. So then that gives us this factor of the square root of 1 minus u squared over c squared. So knowing that momentum is equal to mv, and now we have to change v into proper velocity, we just add this factor again. And then through a lot of other math that we will also not get into, we have this adjustment for energy, which also essentially just includes the factor of 1 over the square root of 1 minus u squared over c squared. Now, back to your question. So when something is moving at a significant speed of light, we have this momentum formula, right? And so the really important part of this formula is the way I wrote it is key. You have to have the factor in the denominator be under both m and v, right? So you can actually separate it so that you have m over the square root of 1 minus u squared over c squared times v, or you can bring the denominator over to v and then just have m on the outside, right? So if u is at significant fractions of the speed of light, the denominator actually starts going to infinity. And when that starts to happen, right, if you put the denominator under m alone, you essentially have this effective mass of infinity as you get closer to the speed of light. So the whole idea of density is m over v, right? But if you have an infinite mass, and then as you approach the speed of light, you have this like also infinitely small volume, you get this immeasurable amount essentially because of the effects. So it's an interesting situation, but you don't have to consider it that way, because you can also consider the velocity is just getting super, super big. But essentially, it's just momentum getting bigger. So now the conclusions from part 2, two important ones, are in order to account for relativistic effects, time measurements are longer and length measurements are shorter for a reference frame observing another in motion relative to it, and that velocity, momentum, and energy are all adjusted by a factor of that. So now, we have some time now to go into interesting results and examples of special relativity. So I don't know if I'll have time to go through all of them, so I'll just choose actually the 2 easier ones to understand. So this is not the easier one to understand. But essentially, I'll just tell you what it is. In special relativity, just given this form of Lorentz transformations, if you have, let's say, two simultaneous events in different positions in your reference frame, according to another reference frame that's moving with respect to you, it won't see the two events as simultaneous. So let's say you have two clocks reading time 0, but at different positions. A moving reference frame, like someone in a rocket, will see the two clocks actually reading different times, when you would actually see them to read both time 0. So if you want to learn more about that, come up to me afterwards and I will explain it to you. But we'll go into the easier of the three, the Muon experiment. The muon is a particle. It is essentially known as a heavy electron because it has the basic characteristics of an electron, but just more mass. And it decays mainly through this process to an electron and to an anti-electron neutrino and a muon neutrino. And so just so you know, neutrinos are also fundamental particles. They were thought to have 0 mass, and then there's this really cool experiment that's done to show that they don't have 0 mass, that they have like a very small amount of mass. So again, if you want to know about that, I'll be happy to explain it to you later. But all we need to know is that this is what it decays to. Its lifetime for this decay in its rest frame, when it's at rest, is 2.2 times 10 to the negative 6 seconds. So now, we have cosmic rays hitting our atmosphere all the time. So accounting for their speed and their lifetime when they are produced in the atmosphere, they would actually not be able to make it to Earth's surface given those conditions. But somehow, we happen to measure them all the time, arriving at Earth's surface. So how is this possible? So we have to consider two different reference frames. Let's consider the ground frame first. You watching a muon making its way down to Earth, essentially. So if we're watching a muon move, right, we know that we have to account for time dilation. We think that the muon's time is passing slower than our time, which means that what happens to its lifetime? It increases, yes. Which means that given its speed and now its longer lifetime relative to us, we see the muons as actually being able to arrive on Earth. But what does the muon think of itself? Well, in the muon's reference frame, we have to account for length contraction, right? So the muon does not think that it's moving, right? Technically to us it's moving, but it thinks in its reference frame that it's still. And it just sees the rest of space moving around it, right? So if it sees the rest of space moving around it, we know that length contractions require that the space itself contracts, right? And so that distance between the muon and Earth actually contracts by just the right amount so that it has time to reach the Earth given its normal lifetime of 2.2 times 10 to the negative 6 seconds. So what's great is that information in both reference frames coincide. Both think that they're arriving on Earth, which is supposed to happen or else physics will break down. And so this is a really interesting effect of both time dilations and length contractions. A wonderful example of how we use it to sort of understand what's happening to us in the real world. So that was the Muon experiment. Now we're going to get into the most interesting part, I think, for you guys of this presentation, which is the twin paradox. So we have two twins. Twin A and twin B decide to try an experiment. Essentially, twin A stays on planet C and twin B departs, goes into space for a while, and then comes back. And so, which is older when they meet again? That's sort of the question of the twin paradox. So, the problem is that the ether theory was disproved. This means that there's no absolute reference frame. So let's think about this. Let's say we're all twin A, and we watch our twin B leave, right? So we think twin B is in motion, so time passes slower for twin B according to us. So when twin B comes back, we'll say, oh, you're much younger than I am. But let's imagine now that we are all twin B, right? Since there's no absolute reference frame, twin B, we think that we're still, right, in the rocket, and Earth is just moving away from us and carrying twin A along with it. So we think that time for twin A is actually moving slower. And that when we come back to Earth and we see twin A will be younger than we are. So twin A will think twin B is younger, twin B will think twin A is younger, but how is that possible? It's not. So that's sort of the paradox, and a lot of people have stated it as this sort of weird thing about special relativity. How are we supposed to explain it? It's impossible. But there is a way to solve it. So the paradox doesn't even exist. It's not even a real thing in the first place. There is no paradox. The reason is because if we go back to Einstein's principles of special relativity, it says that the laws of physics hold to every inertial observer, one that is not accelerating. In this experiment, if it were to be practically conducted, it is impossible for B to move away from A if it did not accelerate, right? But if it does accelerate, our understanding of physics breaks down. So we cannot explain what happens when we're accelerating. And so actually, during twin B's journey, he or she has to accelerate 3 times. One when moving away from twin A and then hanging out in space for a while. And then once, again, to turn around back to twin A, because you're moving in a curve. And then once again to slow down to be able to stop on Earth and say hello to twin A again. So now comes the question. Hold on. And so you'll wonder, okay, let's ignore practicality and just think hypothetically, if we were to have just one, let's say, moving away from the other, and we have this idea, so what would happen? Well, we would have to consider practicality, because even if they were to, let's say, communicate to each other through email or whatnot, they would still think that the other person, they would still have this like not unclear idea of who is younger, right? And so in order for them to actually have this simultaneous reception of information when they meet again at another time, acceleration has to happen. And so this paradox doesn't exist because special relativity or any laws of physics don't hold in this specific case. So now, how do we know which one is actually younger? Well, experimentally. So what some physicists decided to do was they decided to take atomic clocks that are very sensitive to time differences and put one on Earth and then fly one around in a rocket for like a really long time, and then bring it back. And so what we notice is the one that is accelerating is the one that actually is younger. That is the idea, right? So we don't actually understand what's happening when things are accelerating. All we know is that when something is accelerating, there is an absolute reference frame that you have to consider it in, which is something that we can't understand using special relativity, because special relativity states that we have no absolute reference frame. All right, so that was part 3. Essentially, the 3 conclusions that you can take away from this part, building up with the rest of the things, is that events in different places cannot occur simultaneously in 2 different reference frames. We kind of skipped the explanation of that, but that's just sort of the statement and an interesting fact. The other is that the Muon experiment is proof of the applicability of length contractions and time dilations, a very useful one at that, and that the twin paradox does not even exist. It's not a thing. So you can impress people, especially with that one at parties, and say, this does not exist, and I know why. I wanted to talk about why people need special relativity besides, impressing people with the twin paradox idea or detecting muons. So special relativity is really important in particle physics because if we really want to understand particles, we mainly do it through collisions. And collisions of particles can really only happen at significant fractions of the speed of light. Especially as we want to get to creating heavier and heavier particles, we need other particles to collide at higher and higher energies, and higher energies translates to more speed, essentially. Greater fractions of the speed of light. And so if we weren't to account for special relativity, what would happen is we would get results that don't make any sense whatsoever. And so what we do now is then we take special relativity and we use it to understand particle physics, and that can sort of help us understand the nature of the universe as a whole through particle physics and special relativity. So that is it. I hope you enjoyed learning a little bit about it.